Hello, everyone. Good day, and welcome to another session of the Weber Training, the teleclass education series produced in Canada and our neighbor to the north. On behalf of Dr. Saeed Sattar and Paul Weber, our producer and coordinator, I'd like to welcome you to today's teleclass lecture. This lecture is entitled Chlorhexidine Use and Bacterial Resistance, and it's being presented to us today by a good friend of ours, Jean-Yves Maillard, who is professor at the Cardiff School of Pharmacy and Pharmaceutical Sciences in Cardiff, Wales. And I do want to say that this is a highly interesting and important topic because chlorhexidine, especially chlorhexidine gluconate, is increasingly used in healthcare institutions to help reduce things like surgical site infections and so forth. And there are chlorhexidine products excuse me, that may have other uses for antimicrobial prevention and control. What can we say? Dr. Maillard was at the Cardiff University for over 25 years, coming in as a protege to the great Professor Denver Russell, who is one of the giants in the antimicrobial world, and has now risen to professor at that institution. And so with that, let's welcome Dr. Maillard.
Thank you very much, Lynn. Thank you very much for your very warm welcome onto the audience. So when I talked to Paul a while ago, it was very interesting to hear that I could give a talk on chlorhexidine, on resistance, and as Lynn mentioned, that this is certainly a very topical subject, as we know in Europe and elsewhere in the U.S. As well. Chlorhexidine uses has really increased. If you move to the slide number 2, please. In that talk, I'm going to give you an overview. I'm going to give you a bit of a background about a microbicide or biocide use. Then I'm going to talk a bit more academically about how bacteria responds to biocide exposure, and that will give you the background to understand when we're going to talk about chlorhexidine. And then I'll present some evidence about resistance to chlorhexidine so far, in situ and especially in vitro, where the bulk of evidence is. But then at the end of this talk, I'll give you some reality check about chlorhexidine on issues maybe associated with the use or the misuse or inappropriate use of chlorhexidine before I conclude that in about an hour or less. Next slides, please. So let's talk about the background. Obviously, I mean, chlorhexidine is a very important biocide used for antisepsis on disinfection, but it is not the only biocide that is being used. And for the last 20 years, we have seen an increase in the applications on usage of many biocides. If you move to next slide, please, slide 4. And indeed, biocides are used for disinfection, antisepsis, for preservation as well, in quite a very wide variety of product on usage. The largest increase in use in the biocides are certainly with a domestic product. Now you cannot escape a product like a washing liquid, washing up liquid, chopping boards containing a biocide. It's an increase in terms of preservations now in wood and plastic and textiles, and not only for daily use, but also for the heavy industries like the automobile industries, for example. And of course, a huge impact on increasing the use of biocides, and that includes chlorhexidine, will be in healthcare, certainly in disinfections of surfaces, and on antisepsis in terms of skin cleanser, for example. Now, this talk, I'm not going to talk much about antimicrobial surfaces, although they will see that some usage of chlorhexidine will be in coating some medical devices, such as catheters. Next slide, please. So what else do we need to know about why do we need to use biocides and control microorganism surfaces? Well, now it is very well established, like quite a large number, in this case bacteria on this slide, can persist on surfaces, especially in healthcare settings, for quite a long time. On some of those data I've got here, and the persistence, those duration time are not very generous. For example, if we talk on second-line Clostridium difficile on the spores, here it says 5 months, and that's taken from some literature, but I think it's an agreement that really that can last for we can recover the spores for over a year. So here we go. We've got on surfaces plenty of microorganisms that are persisting on surfaces, despite maybe sometimes regular cleaning and disinfection. So we need to take that into account. Now, some of those microorganisms will be really specific, for example, to the food industry, especially the Salmonella enterica, typhimurium, where persistence can last for months, but especially associated with meat, for example, or unclean processes and so on. Next slide, please. So in terms of interventions, that's why we're using biocides for different aspects. If we're looking at healthcare settings, then obviously we want to use biocides on contaminated surfaces. And that's to protect or to decrease the number of microorganisms you've got on surfaces, and to prevent the preventions of those microorganisms to be transferred on the hands of patients or healthcare workers. So the interventions we have at the moment are obviously surface disinfections, liquid disinfectants, with the use of various cloths, antimicrobial pre-wetted product, wipes or towelettes. We've got now very popular UV irradiations following cleaning. And I put gas down here on the right-hand side corner, which is fumigation. Those will be the vaporized hydrogen peroxide and similar devices. At the same time, those biocides, and especially for antisepsis, are used for hand hygiene in terms of liquid gel rubs or now wipes, and that really to decrease or to prevent the transmission of microorganisms between patients, hopefully, but also especially between healthcare and patients. Now, in the red box on the left-hand side, I give you some information here about compliance, and we'll talk about compliance later on as well. On hand hygiene compliance, depending on what review you look at or what paper you look at, it varies between 30 and 85% compliance. And 85% compliance is where the infection control prevention team is very active on basic staff and really listened to them. But in general, hand hygiene compliance is rather low. Now, talking to my friend Bill Rutaline in the US, he gave me some data about surface disinfection compliance, and he estimated that a surface disinfection compliance is about 32%, which is very, very low. So we'll come back to compliance versus maybe overuse later on in this talk. Next slide, please. I should be on slide number 7. What else is in that background? Well, in 2016, a person called Lord O'Neill, which is an economist, provided a report to the British government about the possibility of antimicrobial resistance, on the cost of antimicrobial resistance, and especially microbial resistance to antibiotics. And his predictions, an economist, is in that slide where he's predicting that by 2050 you're going to have 10 million deaths just caused by microorganisms that are resistant to antibiotics, and that will dwarf any other pathology you can have. And the economic consequences is very dear. So suddenly now we know we need to control microorganisms better. On following those reports, now we've got, at least in academia, more sources of money available to look at new antibiotics and new detection tools, and a tiny amount of money to look at infection control and improve infection control. But at least infection control is recognized as a very important tool to control pathogenic microorganisms. Next slide, please. So that leads us to chlorhexidine. And for the purpose of this talk, I did a quick search on a peer-reviewed scientific articles published for the last 30 years on looking at 3 search engines, the Web of Science, Google Scholar, and PubMed. And what I've done here is type the keyword chlorhexidine on resistance. Although that is a bit misleading because some papers dealing with antibiotic resistance on the use of chlorhexidine are not necessarily chlorhexidine resistance, but the image is quite clear. You can see that from 2006 you've got almost an exponential growth of the number of articles dealing with chlorhexidine on the keyword resistance at the same time. So it is very clear that the use of chlorhexidines and papers dealing with chlorhexidine are certainly in increase in the last at least 10 years. Next slide, please. So that brings us to the probably academic part of this talk, is trying to understand the bacterial responses to biocides. Now, if one wants to understand why bacteria become to resistance, we need to look in more detail as to how the bacteria behave when exposed to the biocide, and that includes chlorhexidine. Next slide, please. So you should be on slide 10. Now, it is very well known that different types of microorganisms have different resistance profile to a biocide. Some of them are very resistant, some of them are less resistant to any type of biocide, and that is caused with what's called the intrinsic property of the microorganism, so the natural ability of the microorganism to survive a biocide exposure. So on top of this list, we've got the prions and the bacterial spores that are extremely resistant, and it is not really surprising that spores are used usually as biological indicators for many biocidal processes. And then in the middle, in yellow, you've got a range of microorganisms, and we can start seeing those bacteria, mycobacteria, are particularly an issue, so it's not usually surprising why you've got a product claim, specific claim against mycobacteria, on a Mycobacterium tuberculosis in particular. And then we've got other microorganisms, especially non-enveloped viruses, and we've got vegetative gram-negative bacteria, so that will be the Pseudomonas, for example, which are particularly difficult to destroy. And at the bottom of this list, we've got the gram-positive, so the Staph aureus, Enterococcus, and so on. And according to that chart, those are not necessarily very difficult to destroy with the biocide. Of course, here on the right-hand side, you've got a little insert with exceptions. You always got exceptions depending where the microorganism is from. And by looking at the literature, we know that bacteria isolated from healthcare settings, so clinical isolates, usually environmental isolates, are usually less susceptible than biocide, than their culture collection counterpart. Next slide, please. So slide 11. Now, to understand better the interaction between the bacteria and the biocides, what happens first is obviously all biocides are detrimental for the bacteria. Are they going to cause some damage to the bacterial cells, especially the outer part of the bacterial cells? But what we need to understand is with short exposure or low concentration, those damages are reversible. So that means that if you remove the biocide, the product, then the bacteria will be able to recover. This is a very important aspect of this talk to understand what's going on with chlorhexidine. Now, if the exposure to any biocide is much longer, at the end, the number of damage, the amount of damage caused by that biocide will be irreversible, causing some very profound damages to the cells, and notably a change in internal pH, so the pH inside the cells. And as soon as that pH change, then usually the cells, the bacteria, become unviable, and will die. It will be committed to a cell death. That's why it's called an autocidal activity. But the point of this slide is really to emphasize that short exposure to a biocide, whether it's chlorhexidine or others, will be reversible, rather than the longer exposure should kill the microorganisms. So next slide, please. So cell 12 is really to emphasize that point about reversible event for exposure to biocides. Next slide, please. Slide 13. Also, what we need to understand is bacteria are extremely good at surviving a biocide exposure because they've got a number of mechanisms at the disposal that enable them to survive. In terms of mechanism, you've got the expressions of a very specific mechanism, and I will give you an example in a few minutes. Reductions in uptake and penetrations, we change the outer membrane of the cells so the biocides cannot penetrate anymore, the cells will survive. We've got reduction in accumulation as a specific mechanism, and that will be the efflux pumps, whereby any biocides that manage to penetrate in the cells will be able the cells will be able to get rid of that biocide quite easily with those pumps. We've got also a specific change in metabolic pathways. And we've got also, on some occasion, especially for metallic ions, inactivations, where you've got some specific enzymes that are able to convert the metal ions, which is highly bactericidal, to the metal, which is not. Apart from that, we've got within the bacteria some physiological changes, changing growth patterns, if they grow within the biofilm or community of microorganisms, and that will lead to an increased resistance to a biocide. And what is not really studied is repair mechanisms. Some bacteria are very good at repairing damages, and I did mention that when you've got short exposure, for example, or with low concentrations, then damages are reversible. So if a bacteria is very good at repairing it, it can survive better. Next slide, please. Of course, those expression of specific mechanisms, usually they're encoded by specific genes, and those genes can be transferred between microorganisms. It's why here I put the acquisition of genetic determinants, and you will see what it is, what that matter when we talk a bit more about chlorhexidine. Next slide, please. So to give you some example of bacterial responses to biocide with a very specific mechanism, first one, some work we've done a long time ago, changes in membrane properties. So on the right-hand side, you've got some electron microscopical pictures of a Pseudomonas. This is Pseudomonas estudere in particular. The top picture is a naive cell, if I can say that like this. It's a bacteria that is, those are bacteria that are susceptible to in this case, the quaternary ammonium compounds, but also to chlorhexidine diacetate. On the bottom part of that EM, you've got now cells that have been trained to become resistant to chlorhexidine. The magnification is the same, and you can see the profound change in those cells. I mean, those cells are becoming really large indeed. So when we look in more details at those bacteria, the composition, we could see that those cells that now become less susceptible to chlorhexidine, they've got a different membrane properties, and especially outer membrane protein profile, and those are called the porins, and they're very important for the uptake of biocides. And by changing those profiles, those bacteria are decreasing the susceptibility to those biocides. Likewise, we've got a change in lipopolysaccharide, which is in the outer membrane of those bacteria. So a change in the membrane properties of those bacteria make them less susceptible to the biocides. Next slide, please. This slide refers to a very good review. It's a bit old now, but still really topical, about efflux pumps. Those are pumps that are very active in bacteria and enable the bacteria to get rid of any antimicrobial or the compounds they do not like, and that include antibiotics and biocides. So far, we have identified 5 different families of pumps, and by the rule of thumb, the more pumps that are expressed in those bacteria, the more compounds they can get rid of. So again, we will see how important it is in terms of chlorhexidine in a minute. Next slide, please. Also, a concern, especially with chlorhexidine, is what we need to realize is when we've got exposure to biocides, then it will cause a stress to the microorganisms. And by causing a stress, then bacteria can respond very well to the stress. It's called the general stress response, or SOS response mechanism. That will trigger a global response on the expression of very specific mechanisms such as efflux or a membrane change, a change in lipid compositions, on change in also metabolisms, or increased repair capability. At the same time, a biocide can exert a selective pressure on a microorganism. When we treat microorganisms, we don't treat one microorganism, we treat 1,000 millions of microorganisms at the same time. So the very weak microorganism will be killed, the ones that are less weak will adapt, and that's what the selective pressure come in. In terms of adaptation, the selective pressure will drive somewhat some mutations within the bacteria. So some mutations will enable the bacteria to survive better. On a very common mutation, for example, is in regulator genes, for example, that will lead to an overexpression of efflux. But that is a very narrow response that do occur from time to time with biocides, and that includes chlorhexidine. Next slide, please. Now, we will talk about bacterial response to the biocides, and especially resistance. I mean, this is not a new concept. And for many biocides, then we've got evidence over the years, over the last, in this case, 1958, with a quack resistance to bacterial resistance to quack. So again, this is not a new subject. So we need to bear that in mind. Next slide, please. I had to talk about a definition as well, because from a practical point of view, we need to know what we're talking about. For a scientific point of view, on what we've got in peer review literature, often resistance is defined as a reduced susceptibility, so an increase in minimal inhibitory concentration or an increase in minimal bactericidal concentrations. Practically, that really does not really matter, because that small increase in MIC or MBCs might be not enough for a bacteria to resist or survive the exposure of an in-use concentration of a biocide, which is much, much higher than the MIC or the MBC in general, and you will see that in a minute. So one of the practical definitions that we came up on, and we published that a number of years ago, is a bacterial survival following biocide challenge at the in-use or during use concentration. The in-use concentration is the concentration of the product, and during use, that's the concentration that encompasses the dilution of the product upon use. And I will give you some example later on. Cross-resistance is obviously a huge problem as well, or a concern. It's a bacterial surviving a biocide challenge at the in-use or during use concentration, and being resistant to an unrelated antimicrobial, and that may include antibiotics. And we're talking antibiotic resistance, we're talking about a clinical resistance to that antibiotic. Of course, all the business of resistance, if you move to the next slide, please, is very important, been picked up by regulators in Europe. And now they've published a number of documentations on resistance to biocides. Next slide, please. And also, those documentations have informed what's called the biocidal product regulations that inform manufacturers what documentation they need to show to be able to commercialize the product in Europe. And now part of the regulation really mentioned that the manufacturers need to show that the product will not cause resistance when used. So that's the case in Europe. Next slide, please. But that's also the case now in the U.S. with the U.S. FDA that have published the rules now that apply to triclosan and trichocarban, but also looking now at benzalkonium chloride, benzathinium chloride, and chloroxylene. So again, the business of biocide resistance leading to cross-resistance is an important one. And again, we will talk about that when we talk about chlorhexidine just in a second. Next slide, please. So what evidence do we have about a bacterial resistance to chlorhexidine? So we need to look at what we know about in situ, so that means in practice, and the evidence we've got in vitro, that means what we've done in the lab. Next slide, please. So in the context of using chlorhexidine, then we need to know what the chlorhexidine is used for. And here I'm listing a number of applications. A lot of it is to do with skincare and skin preparations, especially before you're having a preoperative scrub or for a vascular access of site dressings, as you will know. Chlorhexidine is also used on devices, as I mentioned before, in intravenous catheters. It can be coated with chlorhexidine. on needleless IV connectors as well. So we're starting to see that use of chlorhexidine as well. And it's still used also with solutions for oral care mouthwash on urology for bladder irrigations. Next slide, please. Now, in this slide, what I find that in the web, I have to say, on this slide give you a bit more information about potential use of chlorhexidine, give you the concentration at which is used, which is an important one we're going to consider a resistance, but also very importantly, move to the next slide, please, it gives you information about some of the composition of the chlorhexidine formulations. Now, what we need to be clear about that, chlorhexidine product or formulation, they're not used on their own. They're used in a complex formulation that contain other biocides sometimes on different type of excipients. On those biocides or excipient might be very important for chlorhexidine solubility or to potentiate the activity of chlorhexidine. So you can see here some information I have with some usage where we have isopropyl alcohol. The mixture of chlorhexidine on alcohol is synergistic, so you've got much better activity when those two are combined. And you've got mixture sometimes of chlorhexidine on cetrimide, and that's to do with chlorhexidine precipitation, so that prevent chlorhexidine precipitation in a product. Next slide, please. Now, this table give you information about the use of chlorhexidine of product contaminated that contain chlorhexidine and outbreaks. And those are documented information that we can find in the literature. And I put them together in a book chapter that hopefully will appear soon. And here we've got a quite large number of gram-negative bacteria, Pseudomonas, Burkholderia, Ralstonia, Serratia marcescens as well. And all those microorganisms have been found in product containing chlorhexidine, and those products were used, and following that use, we had an outbreak of infection with those microorganisms. But what is interesting in that table, and I've highlighted in yellow what is interesting, is in all those products, it was not pure chlorhexidine. We had a problem, either a problem with the usage of the product, where we had a refilling, so a dilution of the product with a contaminated solution, contaminated water, non-sterile water, use of contaminated bottles, and so on. So very often, when we look at that, is very often what we have, we've got bacteria surviving in a product because the product is not being used properly or not being diluted properly or diluted with a contaminated solution. Next slide, please. Now, very similarly, much earlier, Bill Ritala produced a very, very good review about outbreak associated with a contaminated antiseptics, and that concerned obviously chlorhexidine. And I'll give you here a small table as well with chlorhexidine, the type of contaminant found in those products. And again, the same picture image is where we had contamination in this product. We know because we had an inappropriate use of those products, use of contaminated water, tap water, over dilution of those products, and so on. So again, it is to do with all those evidence of link between chlorhexidine resistance and bacterial growth in chlorhexidine contaminated product is linked to inappropriate usage. So those are the information we've got about the risk associated with chlorhexidine at present in situ in practice, and that again relates to inappropriate usage. We've got, however, far more information about a bacterial resistance to chlorhexidine in vitro. Next slide, please. On next slide, again, you should be on slide 30. Now, we know that when we expose a bacteria to chlorhexidine at low concentration, we're going to change the susceptibility of that microorganism. On this work we've done on quite a number of years ago on Pseudomonas aeruginosa, what we showed is a change in susceptibility profile of those Pseudomonas following a very short exposure to chlorhexidine. I think it was only a 5-minute exposure. So we changed already the profile. And now we know it's because the bacteria is able to respond to that. We're causing a stress with that chlorhexidine, and then the bacteria is developing a number of mechanisms to be able to survive. On the right hand side, a table, what you have is a number of culture numbers. Those are either original Pseudomonas aeruginosa, or some of them have been trained to become resistant to, or less susceptible to chlorhexidine. On the middle line, you've got the original MIC, so 8 to 10 for the sensitive strains, and over sometimes 40 to 70 for the adapted strains. And then when we carry on growing those strains in repeated exposure to chlorhexidine, you can see we can really increase that MIC to chlorhexidine, and this is quite stable as well. So again, here what the experiment we're saying that we can change the susceptibility profile of Pseudomonas. It can be quite stable, that profile, following the use of exposure to low concentration of chlorhexidine. Next slide, please. We've done exactly the same now with Salmonella enterica, and here we've got a table with the first line on chlorhexidine gluconate. The baseline the baseline MBC is 0.01, and after exposure to chlorhexidine at different concentration, we can increase that MBC up to 50-fold. So not only we can increase the MBC to chlorhexidine, but we can also increase the MBC to benzalkonium chloride, so a completely unrelated compound. So here the demonstration of a cross-resistance. Next slide, please. Very often when we find in literature is a question of reproducibility of the data. If we do the experiment once, can we do them again in 6 months' time and have exactly the same results? And we've done that over a year period. And again, those patterns of a decreased susceptibility following the exposure to the same concentration of chlorhexidine is quite reproducible as well. Next slide, please. We've done the same experiment with other microorganisms. Here you've got also buccal diarrhea. And what I'm trying to show here as well is in the case of some microorganisms like this one, short exposure to chlorhexidine will really change the MIC considerably, about a 50-time increase in MIC. But when you passage, or when you grow the bacteria without the chlorhexidine, then those bacteria revert to be very susceptible to chlorhexidine very, very quickly. So what we're showing here is very often when we see a change in susceptibility profile of the bacteria to chlorhexidine, then this is not stable. So if you remove the chlorhexidine, the bacteria becomes susceptible again. So that's very transient mechanisms of resistance. Next slide, please. And we've got exactly the same result with, in this case, Salmonella, a very transient mechanism of resistance. We've got chlorhexidine, they stay resistant, we remove chlorhexidine, they become susceptible again. Next slide, please. You should be on slide 35. Of course, here I did mention a cross-resistance between chlorhexidine and a quaternary ammonium compound. The real issue is possible cross-resistance between chlorhexidine and a chemotherapeutic antibiotics. And in the literature, we've got quite a number of publications, as highlighted in this table, that is highlighting an issue with treating with a link between chlorhexidine resistance or decreased susceptibility, so if talking about an increase in MIC or MBC, on antibiotic resistance, on clinical antibiotic resistance. Next slide, please. And indeed, what we're doing at the moment here in Cardiff, looking at chlorhexidine, but also at carbapenem resistance, what we've looked quite a large number of isolates, about 210 isolates, whether Klebsiella pneumoniae or E. coli, and we looked if there was a correlations between elevated MIC, so an increase in MICs and MBC in those isolates, and increasing in antibiotic resistance, clinical resistance. And we do find that correlation, especially with chlorhexidine, on that little table on the right-hand side, where the blue line show you that correlations. So again, here, the evidence, at least in the lab, tends to show that might be a correlation with bacteria with highly elevated MIC or MBC to chlorhexidine and a clinical resistance to some antibiotics. Next slide, please. Of course, then is a very important subject. On quite a number of papers have really looked into that as well. On this table is just an extract of some information for different microorganisms, where you've got sometimes highlighted a chlorhexidine. So, for example, if I look at E. coli, treatment with chlorhexidine at 0.004%, so very low concentrations, we might have no change in MIC MBC to chlorhexidine, but we've got now a change in antibiotic clinical susceptibility profile to a ticagrelin, ampicillin, and tobramycin. And if we're looking at that table in different parts, it's sometimes the same results. We might not necessarily have an increase in MIC to chlorhexidine, but we will have a change in antibiotic susceptibility profile. And some of the studies have looked and trying to understand why the change was driven by, and very often what they find is expressions, overexpressions of efflux pumps, those efflux pumps I was mentioning earlier on. So it seems that with chlorhexidine, resistance and cross-resistance to clinical to antibiotics, the efflux will be very important. Next slide, please. Now, this a very interesting paper, again on chlorhexidine, looked at the effect of chlorhexidine on salmonella as well. And what those researchers found as well is not only you've got some specific mechanisms being overexpressed, but you've got quite multiple mechanisms all together being expressed. And the phrase they're using is they've got an implication of a defense network that enable the cells to react to that exposure to chlorhexidine. And very often in this field, when we look and we talk to researchers, they're thinking, well, we've got those bacteria have got only one mechanism to survive biocide exposure, but in fact, they've got quite a number of those mechanisms that are working together to give them that very low susceptibility to those biocides. Next slide, please. So as I was mentioning to you the importance of looking at efflux, on this slide here, again, from the literature, we've got correlations between elevated chlorhexidine, MICs or MBCs, on what's a efflux pumps genes on carriage of efflux pumps. And those in that table are clinical isolates. And what it shows very clearly is all those isolates from the clinical environment, whether they're blood isolates or environmental isolates, not only they've got a elevated MIC to chlorhexidine or MBC to chlorhexidine, but they also all carry efflux genes. And you can see, for example, the first line here, we've got a quite well-known genes called the QuAC-AB efflux pumps, and 83% of those isolates carried this gene in that study and so on. So again, when we're saying the picture that's emerging now is all the isolates that show low susceptibility to chlorhexidine, all those isolates from the clinical environment, we're trying to find all those efflux pumps they carry. Next slide, please. And this paper is not different. This paper was concerned a 53 high-level puricin-resistant MRSA, and what they found is 83% of them had an MIC for chlorhexidine 4 microgram per ml, which is quite high for those type of microorganisms. I mean, at the same time, not surprisingly, they're looking at killing the microorganism, and what they found is when you mix the microorganisms with organic load, then you don't kill them very effectively. Next slide, please. Still from the same paper, what was fascinating about this paper is not only those isolates can carry a efflux pump genes, but they can carry multiple efflux pump genes. So if you're looking at a small insert on the right-hand corner which said multiple gene carriages, then you can see that at least some isolates, 76% of the isolates are carrying multiple genes, and all those genes encode for separate efflux pumps. And as I mentioned earlier on, the more efflux pumps you have, and the more efflux pumps that are expressed in the bacteria, the better they are at surviving a biocide exposure. Next slide, please. Very recently as well, and I just picked it up yesterday or the day before, about the prevalence of they call a QuAC resistant genes in MRSA isolates, and you can see the huge increase of those prevalence as well, which making the point. Next slide, please. So what we have so far is we know that exposure to chlorhexidine will change very quickly the susceptibility profile of the isolate, but that's measured by minimal inhibitory concentrations or minimal bactericidal concentrations. We know that loads of clinical isolate that got an elevated MIC or MBC to chlorhexidine will carry all those resistance genes, especially efflux pump genes. We know that there's a worry that those isolates with elevated MIC and MBCs have some correlations with clinical resistance to a number of antibiotics as well. But I think we need to take a step back and have a reality check now. So please, next slide. On next slide again, it should be on slide 44. Now, those different tables are what you find in textbook about the MIC of different microorganisms to chlorhexidine, particularly to chlorhexidine gluconate in this case. And you can see whether they are gram-positive bacteria at the top table, gram-negative bacteria, and even fungus or yeast. You can see the MIC. Now, next slide, please. Now, in that purple table, you can see I put down the application on at which concentration chlorhexidine is being used. And I think it's very clear by just looking at that table is by far, for the majority of those applications, the concentration of chlorhexidine excess by a large amount the concentration at which the bacteria is inhibited. So if those actually concentrations are used in practice, then really we shouldn't really have a problem with bacteria surviving the effect of those products. So where is the problem? Next slide, please. Well, in terms of a reality check, we need to look at how the product is used. On the table earlier on, I show you about product contamination and outbreaks. Highlighted quite a number of inappropriate use of those products. So we need to really look at the factors that affect the efficacy of chlorhexidine. And you've got factors inherent to the product, factors inherent to the microorganism, and factors also inherent to the use of the product. Now, if we're looking at the factor inherent to the product, concentration is very important. So basically, it's not a brainer. The higher the concentration is, the more efficacious your product is. However, with those type of products, especially with skin products, you can't use such a high concentration because obviously you're going to have problem with contact dermatitis and so on toxicity. Also, using high concentration of chlorhexidine, it will precipitate. And that obviously is not very good because the chlorhexidine available to kill the microorganism will decrease as a result of precipitations. Now, in terms of efficacy, we've got a way to measure the efficacy of a typical specific biocide. It's called the concentration exponent. The concentration exponent gives you an idea of if you dilute or decrease the concentration of that biocide, by how much I will decrease the efficacy of that product. So we look at the chlorhexidine. Normally, the concentration exponent is 2. So that means if I'm diluting a chlorhexidine product twofold, I'm going to lose the efficacy of the product by a factor of 4. So not too bad in terms of chlorhexidine. Other products, obviously, ethanol-based on others, or a phenolic like triclosan, are much, much worse. But again, concentration is very important. Next slide, please. Formulation is extremely important in terms of chlorhexidine, and very often manufacturers forget about incompatibilities. The use of chlorhexidine with an anionic surfactants will decrease the activity of chlorhexidine. With viscous material, with other type of product, but also with the bottle as well. Cork, for example, will really reduce the efficacy or the activity of the chlorhexidine. It's highly incompatible. So again, very often we find that the manufacturers forgot about that. And then even if they said we've got 2% solution chlorhexidine and product of 4%, then because you've got so many incompatibilities, and in fact the in-use concentration of what you really have active would be far, far less than that. As I mentioned, we've got precipitations. On chlorhexidine precipitate very well, especially chlorhexidine diacetate. So it's why usually gluconate is preferred, but still chlorhexidine gluconate will precipitate, especially with mixed with tap water, hard water. So if you dilute a chlorhexidine concentration or a product with tap water, you might have a precipitation. And that's why, as I said, you're using citramide to avoid those precipitations. Next slide, please. Factors inherent to the application. Organic soiling is very important. On chlorhexidine is inactivated by organic load, by soiling. So blood, vomit, feces, or whatever organic matters you might have. So again, we need to bear that in mind during applications. Next slide, please. Factor inherent to the use of the product. The actual exposition times. Again, that's part of product usage. Very often, if we use a product, if you use, for example, a wipe, it's 10-second type on the surface, or to wipe the skin area of the patient is going to be 10 seconds, a very, very short contact time. So that's not going to be very good. So again, by a rule of thumb, the longer the exposure time is, the better the activity will be. And again, we're back in the scenario about that a reversible damage caused to the bacteria. If the concentration is not high enough or the exposure time is too low, then the bacteria will be able to recover very nicely. Next slide, please. And I mentioned dilution during application. Again, that was absolutely clear with all those examples of contaminated product with bacteria. Next slide, please. Of course, when we talk about resistance as well, what is interest for regulators but manufacturers as well on end users is my product going to cause a resistance to antibiotics or to other biocides? And it's quite difficult to predict resistance and cross-resistance to a biocide. So you've got very few methodology to do that. And I'm going to describe one to you in the next couple of minutes. Next slide, please. We should be on slide 52. And the way that protocol works is based on a determination of MIC and MBC. And following the usage of your product, if we don't have a change in MIC and MBC, so if I've got a chlorhexidine product, if I don't have a change in MIC and MBC, I'm going to look at specific antibiotics. If I don't have a change in the susceptibility profile to those antibiotics from susceptible to clinical resistant, then we don't have any problem with the use of the product. Now, the important part of this protocol is we're using product at the during use concentration, and we'll explain that just in a second. Now, the next part of this protocol, next slide, please, so slide 53, is if you've got a change in susceptibility profile, either for the chlorhexidine or for the antibiotics, then we really need to look at if we've got if that change is stable or not. Next slide, please. If the change is stable, then we've got a problem. Here we've got a resistance is highly likely, so the recommendation is not to use that product at all. Next slide, please. However, if that change is not stable, what we are now, we've got a transient resistance. That's what I was explaining to you early on. So we've got transient resistance. We've got what's called potential risk. So if we know that the product is used constantly, and you always got that product on the surface of the skin, then yes, we're going to have a problem here because that resistance, that change in susceptibility in that microorganism is not going to go away at all. If the product is that does not persist on surfaces, then usually we don't have any problem there. In this transient resistance, then as soon as you remove the product, the bacteria becomes susceptible again. Okay. Now, in the case of chlorhexidine, as you will know, most manufacturers, as part of the product claim, saying that lasting effect of chlorhexidine solutions. At a low concentration, it will persist in skin, persist in surfaces at a very low concentration. So if you've got a problem with the chlorhexidine, that we change the susceptibility profile, and we need to change the stability of that profile, that we would know that we might have problems with chlorhexidine because we've got residual concentration on surfaces. Next slide, please. So to give you some examples of usage with chlorhexidine, we've done that work, obviously, on what we find exactly, as I said, with chlorhexidine is we've got this type of profile where we know we're changing the susceptibility profile of the microorganisms, but this profile is transient. So if we haven't got the selective pressure, then it doesn't matter. But if we've got that selective pressure, so a concentration of chlorhexidine remaining on the surfaces, then we will have a problem. Next slide, please. Now, we've used some real product. On this one was a mouthwash, for example, at the during use concentration. So we're using a product, but as we use it, it's being diluted. It's a mouthwash, and we estimate that the dilution is 1 in 40. So we're using a very low concentration of chlorhexidine. And you can see that even at that low concentration of chlorhexidine, then there was no issues with it at all. So in this case, with that test, our test is showing that you can use that mouthwash. There will be no risk for developing resistance. Next slide, please. So what are my conclusions about chlorhexidine? Hopefully I haven't confused you too much. Next slide, please. On next slide, please. We should be on slide 59 now. Very obviously, a dead bacteria cannot become resistant. And that's the truth, and that is important to consider, and that's what we're aiming for. So when we're using a chlorhexidine product, we want to kill the microorganism. If there's no survivor microorganism, they cannot become resistant. Next slide, please. Reality check as well, conclusions. As I mentioned, very often, those are formulations. They are complex formulations that need to make quite a number of criteria in terms of low toxicity if using on skin. Make sure it's not irritation as well, so you need to lower the concentration. We'll add some excipients so it make it more manageable to use on skin. Those products have also other performances as well, especially cleaning performances, where you can have a detergent action as an antimicrobial action. At the same time, we've got organoleptic properties. If the product smells very nice, for example, and so on. So overall, those formulations are quite complex. And from time to time, as I mentioned, we can add other biocides with chlorhexidine. If we use ethanol, it's synergistic, so we've got much better efficacy. So we can decrease the concentration of chlorhexidine we're using and retain the same activity, which is very good. But sometimes, if we've got other excipients like anionic surfactant, for example, because we want to have a very good cleaning ability, we will decrease the efficacy of chlorhexidine. So again, when we're looking at the product, we have to be very, very careful. Next slide, please. Of course, here the conclusion is, at the start of my talk, I said, well, compliance for hand hygiene, compliance for disinfection surfaces is not very low. At the same time, in terms of chlorhexidine, we know that chlorhexidine now is being used for absolutely everything, at least in hospitals. So I think we need to have a right balance of buying what is used on what for. As for one, I am not in favor of using chlorhexidine for absolutely everything. We've got other biocides available that would do a very similar job on avoid using that chlorhexidine. Next slide, please. So slide 62. Overall, in terms of conclusions, what really I have is using the product. It's not because the product is going to say it's going to kill the bacteria and it does what it says on the tin that is going to work. I mean, the usage of the product itself is important. As we mentioned, compliance is very important. The product efficacy, so inherent to the product, that's obviously important to do. The product usage, so is it being diluted? Are you reusing the product? And so on will be extremely important, especially in the case of a chlorhexidine-based product. And an understanding, obviously, of the factor of efficacy will obviously be important for you to understand is, am I using that chlorhexidine product properly? If I dilute it, what's going to happen? If I'm using it really where you've got heavy soiling, so before cleaning, then that's not going to work at all. So again, with a conclusion of that talk is we're using a formulation. We have to be careful about this formulation. Using the product properly will avoid quite a lot of episodes of resistance. However, what is worrying, and what we've seen more and more in the clinic, is all those those bacteria isolates carrying all those resistance genes at the moment, and we need to know more about the consequence of that and the effect of that. Right, next slide, please. So that's the end of my talk. I'm sorry, maybe I was talking a bit fast. I'm trying to catch up time for me not being here on time. So thank you very much for listening to me, and to you, Lynn.
All right. Thank you so much for that excellent lecture. It is a very complex topic, but I think your summary slides summarize the very, very important points about overuse, proper use according to instructions, and the importance that the dead bugs don't carry resistance, or they don't promote or require resistance for that matter. So let's give our thanks to Dr. Jean-Yves Maillard for his presentation today, and thanks so much for joining us. I do want to point out on the following slide after his those pictures of his institution there in Cardiff, we have a few free European teleclass lectures coming up. These are broadcast live from the 2018 IPS conference, and they're both very excellent lectures, again, on disinfectant issues and surveillance issues as well. In October, on the 11th, is the free CBIC teleclass. Infection Control Champions Are Made, Not Born. We'll have a speaker named in the future. And on the 17th and 18th, additional teleclass lectures, again, important topics for disinfection of surfaces, environmental, infection control, and so forth. They're sponsored by Gojo, as you see down below there on the screen, and we welcome their sponsorship. When you see the last slide, the patron sponsors for the teleclass education series, Diversey, Virox, Gojo, and the World Health Organization, and we thank them all for supporting this excellent means of sharing information and education to the world. And with that, I think we can say we will see you all virtually next time for the next teleclass in the Weber Teleclass Education Series. Thanks again. We'll talk to you soon.